In this screencast, we will learn about XML, the Extensible Markup Language. XML is a text-based language for representing arbitrary data. Because it's text-based and it's well-formed, it's also hierarchical, it makes it really useful for data storage and exchange, especially when the data is relatively small. In this screencast, we will discuss XML and learn about the JAXB API for manipulating XML data. The content that you'll see in this lecture is pretty old. These APIs are approaching 20 years old, and at times they can seem a little clunky, especially by modern standards. However, they do provide some good examples of important patterns and abstractions in object-oriented programming. So first off, we'll get an introduction to XML. We'll see what the language is like. We'll also talk about something called the Document Type Definition, or DTD. DTDs provide a format for the XML schema. They describe what the XML looks like, and so you can determine whether or not a particular piece of XML data is well formed and meets the specifications that the consumer of the XML expects. We'll also talk about the Document Object Model, or DOM. And this is a set of APIs, a representation of hierarchical document-based data like XML. So XML is a text-based language that, like HTML, uses tags to represent data. So here's an example of what XML looks like. Well-formed XML begins with a header, this question mark XML tag that specifies the version of the language that you're using and also how the file is encoded. So a program that reads this XML knows what to expect. This XML chunk defines a person, and it does that with the person tag, and the tag has an attribute called shoe size. Every person has a shoe size. In this case, it's 10.5. The next line of the XML is a comment. Comments begin with less than bang dash dash. Every person has a name. And comments ends with dash dash greater than. After that, there's a name element, which is a child of the person element. In this case, the name is Dave. Now the element tags have a begin tag and an end tag. So we saw on the second line, there's person, the beginning of the person tag, and then we end the person tag with greater than slash person, the name of the tag. Note also that it's possible for an XML element to not have any sub-elements. So you can have a person tag that just begins with less than person, and then immediately ends with a slash greater than. Now, unlike HTML, which a number of you might be familiar with, XML documents are said to be well-formed, which means that each opening tag must have a closing tag. HTML is purposefully tolerant of malformed data. This makes a lot of sense with the web, especially the early web, when people were crafting HTML by hand and didn't necessarily know all of the rules. XML, however, is meant to be for data exchange, and so it's important that XML documents are well-formed because we want the consumers of that information, whether it be a person or whether it be a program, to be able to understand what the rules are and easily and quickly comprehend the data being exchanged without a lot of exceptions. So just to reiterate, XML data consists of elements, like person, and attributes, like shoe size. Attributes are simply name-value pairs associated with elements. Now, why is XML interesting? Why would you want to use it? Well, XML is in plain text, so it's not a binary-based data format, which means that it can be pretty easily read by humans, and also by a number of different tools. Unlike HTML or other markup languages, XML tells you what kind of data you have, not just how to display it. So when you're working with the XML data, it's easier to extract the information that you want. Things are in a well-known location, and you can have an idea of what to expect from your data. The fact that XML is well formatted means that it can be processed safer and easier. You don't need to worry about encountering unexpected data, missing data, and you don't need a lot of extra branches in your code to account for malformed data. XML is also hierarchical in nature, which means that you can search it more efficiently, you know what the structure is, and it's also a natural fit with objects. You'll probably notice that elements and attributes are a lot like objects and fields. Now, XML is not tied to any particular programming language or programming language community. It was designed to be an industry-wide standard that has acceptance across a number of different platforms and languages. In addition to the data format itself, there are a couple of fundamental APIs for accessing XML data. There's something called the SAX API, or the Serial Access to XML Documents. This is an API that allows for very fast parsing of XML documents and allows XML documents to be handled in a very memory-efficient way. There's another API called DOM, the Document Object Model, which models an XML document as a tree of objects. So this is very convenient for object-oriented programming languages like Java. There are also a number of other standards out there for sharing data. So whether these are data formats that are expressed in XML or tools for converting XML into other representations, such as HTML, PDF, other kinds of documents. The XML standard was developed about the same time that the internet was really coming online, and a number of web services leveraged XML as a means of communicating over HTTP for exchanging information on the internet. And because XML is so ubiquitous, there are a number of organizations that are working to improve not only the XML-based language, but then also all of the data formats that are expressed in XML. One of the fundamental questions that must be answered when working with XML is how you model your data. And XML provides two fundamental concepts that we've already covered, the element and the attribute, for representing data. So when should you model data with an element, and when should you model data with an attribute? Well, elements are appropriate for data that contains substructures. Like we saw, a person has a name. There's a substructure relationship. When you have data that's large, so for instance, long lines of text, or data with many properties. If you have data with a lot of variation, something that changes frequently or has a lot of different values, that's a good use for an element. If you have data that is meant to be displayed to a user, you might want to start with an element. And most generally, if you have data that is the contents of some container, that's an appropriate use for an element. Attributes are best for different scenarios, such as when you have data that is small or it rarely changes. Maybe it has a fixed set of values. If you have data that is meant to be used for processing the document, not necessarily things seen by the user, it's another case for an attribute. Or more generally, if the data is a characteristic of some container. One of the challenges with XML is that XML is represented as text. And so there's some special rules that you need to be aware of when representing certain kinds of text in an XML document itself. So for instance, you've seen special characters like less than and greater than. What if you want to have less than and greater than characters in your XML itself? Well, one of the fundamental data types in XML is something called character data. And character data is a literal string. So if you have a less than symbol inside character data, then it won't be considered an XML less than, it'll just be the character less than. So if you have an attribute of an XML element that is of type C data, it can have textual values. And C data is always put in a single or double quote. Parse character data, or PC data, is parsed by the XML parser. So when the XML parser sees a less than symbol, it assumes that it's the beginning of an XML element. So if what you want to represent is the less than character, you must escape the less than character with a sequence like ampersand LT semicolon. This is a lot like escaping new line characters in C or C++ strings, right? You need to use \n. If you have an element, like the name, for instance, in the example person, that contains text, the type of that element must be #PC data. PC data is essentially freestanding text in the XML document. So here's an example that uses both escaped and unescaped greater than symbols. So you have an expression element, and you have an attribute called short, which would be the short representation of it, and there you've got double quote x greater than 5. Because short is an attribute of an element, that's character data, that's C data. And so there you don't need to escape the greater than. However, there's a child element of the expression element called display. And the intent here, this is a kind of a longer piece of text. And so there, we do need to escape the greater than symbol. That's parse character data, because it is the child of another element. It's not an attribute. So XML itself is a language for representing data, but what about the structure of the data that's being represented? One way to describe the structure, and describe it in a way that can be enforced by an XML parser, is by using a document type definition, or DTD. And many XML documents will leverage a schema, a DTD, for describing how they should be formatted. DTDs specify the kinds of elements, so the tags, that may appear in an XML document. It also describes what their attributes are, and in some cases, the particular values the attributes may take on. When an XML document is parsed, its DTD is consulted to ensure that it is structurally correct. And if it's not, the parser will generate an error. This is valuable because you can have well-structured XML data whose structure is enforced by a parser. And because DTDs are a standard, you as the programmer can rely on the parser to detect errors in the XML. You don't need to do that error checking yourself. Admittedly, DTDs are a little clunky in places, and it's not overly easy to use. Here's an example of what a DTD for that person object that we introduced early on would look like. DTDs have a language of their own, which is a little different from XML. Once again, DTDs have that XML declaration, but then it's followed by definitions of elements and attributes. So less than bang element describes an element. Here it will be the person element that has one child, name. And the children of the element are described in parentheses. To describe the attributes of an element, you use the less than bang at list word to describe here that a person has a shoe size, and the shoe size is character data. We'll explain what pound implied means on a future slide. And finally, we describe the name element as being parsed character data. So there, the name element doesn't have any structure beyond the fact that it contains a string, parsed character data. A DTD looks a little like an XML document. It's got one of those XML declarations, and it has the element and attribute list. You can use some qualifiers on the children of the XML element. Question mark qualifier means that the child element is optional. You can have 0 or 1. If you want 0 or more than one of those children, use star. Plus 1 or more. And if there's an either or relationship between the children, use a pipe. If the children have a certain order, you can use comma to say one child follows another. We already saw an example of parsed character data. And if you have an XML element that is empty, it has no children, then you use the empty keyword in your DTD. And do note that an element name can be defined only once in a DTD. Multiple declarations of the same element will result in an error. As we saw in that person example, the attributes of an element are specified by the @list tag. Each attribute of an XML element is described by 3 values: its name and its type, and something called a specification. The type of an attribute may be something like unparsed character data, C data, or the type may specify the specific values that are allowed for that attribute, such as red, blue, or green. Specification of an XML attribute states if the attribute is required, and if so, how is it required. So a specification of pound required means that the attribute must be specified. Pound implied means that's not required, and that's okay for the application, the code that parses the XML data, to have a default value. You can also specify the default value in the DTD itself, right there. And there's also a specification called pound fixed, which means that if the value is present, it must have the specific value in the DTD. I won't go into detail here, but you can also define tags inside your DTD called entities, which are basically macros that are expanded in the XML document. The mechanism looks a lot like the escaped values of a greater than and less than in XML files. To dive a little bit more into DTDs, we will model a phone book that contains entries for businesses and residences. In this model, each resident has a first and last name, an optional middle initial, an address, and a telephone number. Residents may also be marked as unlisted. Each business has a name, an address, and a telephone number. An address consists of multiple lines of text, giving the street address, an optional apartment number, and a city, state, and zip code. Each telephone number has a 3-digit area code and a 7-digit number. And so based on that model, here's what a DTD might look like. After the XML declaration, you declare your phone book element. A phone book consists of multiple, because of the star, residences and businesses. Each resident consists of a required first name, an optional initial, last name, address, and phone. Residents have an unlisted attribute that can have a value of true or false. And we say implied because if the XML data doesn't specify an unlisted attribute, we can imply a value of false. A business in the XML document consists of a name, an address, followed by a phone. A name is just free-form text, so it's parsed character data. And a first name and a last name are both names. An initial is also parsed character data. Now an address consists of one or more street lines, an optional apartment, a city, a state, and a zip code. And note that address is shared by both businesses and residences. Street, apartment, city, state, and zip are all parsed character data. They're all just strings. We don't specify any more structure to them than that. Now phone is a little interesting in that it doesn't have any child elements. So a phone is empty, the phone element is empty. But what it does have is it has 2 attributes, an area code and a number, both of which are arbitrary text, are data. And both of them are required. It's interesting to note that DTDs don't allow you to specify additional requirements like an area code should be 3 digits, and a number should be 3 digits followed by a dash followed by 4 digits. It's beyond the scope of what a DTD can do, and one of the reasons why DTDs might not be appropriate for all kinds of data. If you want that kind of validation in your program, you'll have to do it yourself. DTDs are separate from XML documents. It only makes sense. You want to define your DTD once and then use it for multiple XML documents. In your XML document, you use the <bang doc type tag to specify the root element of the document and also the DTD that describes the format of that XML document. With regards to the XML document, a DTD is something called an external entity. It lives outside of the document itself. And you can specify the DTD using a system ID or a public ID. Or you can have both, actually. The system ID specifies a URL or a relative file name for the DTD, if it lives on the same file system or if it lives someplace on the internet. So here's an example of starting a phonebook XML document that conforms to the phonebook.dtd specification. So you say >bang doc type phonebook, and you say in all caps system phonebook.dtd. You can also use a URL for your DTD as in the following example. There, it's still a system entity, and there's the URL. Public ID uses something called a URN, a universal resource name, for describing the DTD. So here's an example of an XML document whose doc type is a public ID, and then it has this interesting name that begins with dash and has some slashes in it that describes the DTD. We also provide a URL, but mainly just for backup. When an XML processor sees a public ID, it can then correlate that public ID to something perhaps like a local copy of the DTD, maybe it's shipped in the same jar file, and that'll prevent it from having to go download the URL. A couple slides ago, we saw the DTD for our phonebook. Here's what an XML document that conforms to that DTD looks like. After the XML declaration, we have our doc type. The doc type specifies that this document has a root element of phonebook, and it conforms to the DTD identified in the phonebook.dtd file. And just like we described, there's a phonebook that consists of residences and businesses. And here's some XML that conforms to the structure that we defined in our DTD. So that's an introduction to XML. That lets us create XML documents that conform to a certain structure specified in a DTD. Now let's talk about some APIs for working with XML in the Java programming language. The World Wide Web Consortium, or the W3C, is an international standards body that is responsible for XML and other standards for the internet. With regards to APIs, the W3C has published several interfaces and abstract classes that model and manipulate XML. There are Java classes in a package called org.xml-sax, which is a simple API for XML. This API provides event-driven serial access to XML data. There's another package called org.w3c.dom, which specifies the document object model. This API represents XML data as an object graph. Now these are just APIs. Again, these are interfaces and abstract classes. It's the job of some vendor, either a commercial company or an open source organization, to implement these interfaces to provide full functionality. A couple of years after the W3C introduced their APIs, people across the Java ecosystem realized there were some things missing. And they created a new set of standard APIs called JAXP, the Java APIs for XML parsing, that fill in some of the gaps. So there are APIs in the JavaX XML parsers package that provides an interface for vendor implementations of XML parsers. There's also a standard set of APIs in the JavaX XML transform package that transform XML into other formats: text, HTML, PDFs, Word documents, all using something called the Extensible Style Sheet Language for Transformations, or XSLT. Let's talk about the simple API for XML. Sax provides what's called serial access to XML data. How you as a programmer interact with this API is that you provide an implementation of what are called callback methods that are invoked as the XML data is parsed. Now, callback methods are something that you see a lot in computer programming, and we'll see it again when we talk about user interface development. They're basically a piece of functionality that a user provides to a third-party API or piece of software that then is invoked by that black box. Because it provides serial access, the Sax API is very fast and very memory efficient, but it's not always very natural, and it makes the programmer do a little bit more work than would be expected. it does not allow for easy navigation within the document. Once a piece of the document has been parsed, it can't easily be revisited. There are Java APIs like Sax Parser Factory and Sax Parser that are used to parse XML using Sax. Part of the Sax API are standard classes like content handler, error handler, and input source that provide inputs to Sax parsing. Sax API also contains exceptions that are thrown during parsing, like Sax exception and Sax parse exception. XML parsers leverage something called the factory pattern for specifying an interface and separation of duties between the code provided by the API and the user of the API. So the standards organizations specify an interface for parsing XML, but there's some other third party that actually implements it. However, as the consumer of these APIs, you shouldn't know about the implementation. Why do you care about the name of the class that actually does the work when you're programming to the interface? XML parsers also use something called the factory pattern to encapsulate their configuration and creation. So when it comes to creating a parser, you don't invoke the APIs directly. Instead, you rely on a factory object that knows how to create and configure the parser. This not only hides the details of creation, it means that you don't have to invoke constructors directly, but also allows all those details to change out from underneath you in newer versions of the implementation. Now, there are some things about the implementation that can be exposed to the factory, and one of the mechanisms for doing that is by setting what are called features on the factory, which are simply key value pairs that are sent down to the implementation. So let's take a look at an example of using the factory pattern to obtain a Sax parser. The JavaX XML parsers package contains a bunch of classes and interfaces for parsing XML. There's something called a Sax parser factory that in turn creates a Sax parser. As I said, there are ways to set features that configure what kind of parser is created, and you can configure the factory to create Sax parsers that enforce strict validation of the XML that's being parsed against its DTD. After you've configured the factory object, you invoke new Sax parser that will do all of the work to create the Sax parser you had configured. If something about the configuration isn't correct or supported, a parser configuration exception is thrown. One of the interesting things to note about these APIs is that their constructors are protected. Of course, every object must have a constructor, but it doesn't necessarily mean that the end user of that object should invoke it. Instead, this enforces the factory pattern by hiding the implementation of the constructors and even the invocation of the instructors inside the vendor-specific code. Once you've created your Sax parser from the Sax parser factory, you can parse XML by invoking one of the parse methods that are available on that Sax parser. The API supports XML data coming from several sources. It can come from a file or an input stream. Note that these are the standard Java file and input stream classes. This is a great example of code reuse. The authors of these XML parsing libraries didn't deem it necessary to create new classes to represent files and a stream of byte data. They reused classes that were already there. You can also parse XML data from something called a URI, a Uniform Resource Identifier, which is kind of like a URL. Or you can parse XML data from something called an input source. Here is where the authors of the XML APIs decided they did want a new abstraction for the source of XML information. You can create one of these input sources and set things like a system ID for the DTD. That will help it find things like the external entities, such as DTDs. Now, I mentioned that the Sax API leverages something called callbacks. These are methods that are invoked by the parser during parsing to alert the consumer of the XML that certain parts of the document have been parsed. There are several callback interfaces like Entity Resolver, DTD Handler, Content Handler, and Error Handler that are called back under different scenarios. For convenience, the Sax API provides a class called Default Handler that provides no-op implementations of all of the methods defined by those callback interfaces. As I said before, the XML parser is implemented by some vendor, either a commercial vendor or an open source community. And this is code that you really don't need to worry about what it does, as long as it follows the rules of XML and the Sax API. So you can think of it as a black box. You provide several pieces of information into that black box. One is the XML document, which is represented as an input source. And then you also specify the callback handler objects that should be invoked during parsing. If some error or exceptional condition occurs during parsing, the XML parser will communicate this back to the caller via an IO exception or a Sax exception. Now let's take a deeper look at some of the APIs that are involved with Sax parsing. Content Handler is an interface that contains callback methods that are invoked as the XML document is being parsed. So as the XML parser encounters various parts of your XML document, it'll invoke methods like startDocument to indicate that it just started a document, or startElement, that it saw the beginning of a new element. The startElement method has an argument that's of type attributes that describe the attributes of the XML element that was just started. EntityResolver has a method called resolveEntity that is invoked when the SAX parser is looking for some external identity. The resolveEntity method is provided the public ID and or system ID that resides in the XML document. This is how you can intercept requests for external documents. So for instance, you can look in the local jar file to see if a DTD with a given public ID or system ID exists, and if so, you can load it and return it. There's also an interface called DTD handler, which has callback methods that are invoked while working with DTDs. This is not something that's widely used and not something we're going to use in this class. Error handler, on the other hand, is something we are definitely going to use in our XML parsing code. Error handler contains methods that are invoked when something bad occurs while parsing your XML content. What error handler allows you to do is handle errors in different ways. So for instance, if your program is a command line program, when an error occurs while parsing XML content, you can simply log an error message. Or maybe if you're writing a graphical user interface, you want to pop up an error dialog. It's very important to note that by default, the APIs do not record any errors. So it's really important to register your own custom error handler. There are 3 methods on the error handler interface, each of which is invoked with a SAX parser exception object that contains the line number and column number of the XML file that was being parsed when the problem occurred. The 3 methods on the error handler interface describe the severity of the error encountered. So the warning method is invoked under situations like the parser encountered an element that is not declared in the DTD, or maybe you have a DTD that contains multiple declarations of an element. Depending on your program, you might wish to tolerate these conditions. The error method of an error handler is invoked when a recoverable error is encountered. For instance, maybe you have a portion of your data that does not match the encoding. This is something you might want to recover from, handled differently. The most severe error is called fatal error, and fatal error is invoked when you have a non-recoverable error. So for instance, the XML is not well formed, there's an encoding that isn't supported and can't be processed, those kinds of things. How exactly you handle errors encountered during parsing XML is highly dependent on your application. But in many cases, you'll just want to rethrow the SAX parser exception, or perhaps wrap it in another exception type that's more germane to your API. Here's an example of a SAX parser. We have a class called printPhoneNumbers that extends default handler. Recall that default handler is a class that provides no-op implementations of a number of SAX callback APIs, including content handler. This class overrides the startElement method of default handler, which takes several parameters. Something called the namespace URI, the local name, the qualified name or Q name, and then the attributes of that element that's encountered while parsing the XML content. Our implementation of startElement simply determines whether or not the element that has been started is a phone, and if so, it uses the methods of the attributes object to obtain the area code and phone number attributes of the XML element being parsed, and then it prints out those values. Our printPhoneNumbers class also overrides the error handler methods. So if a warning, error, or fatal error occurs, it simply prints it out. Probably not what you'd want to do in real code, but this is good enough for an example. The main method does the work of creating a SAX parser and parsing the XML. The first thing it does is it obtains a SAS parser factory to get a SAX parser. It does this by invoking the static new instance method of SAX parser factory. Once it has the factory object, it says we want to be validating, meaning that we want it to strongly enforce the structure associated with the XML file. And then we call the factory's new SAX parser method to actually obtain the parser. Errors or misconfigurations in the factory will be expressed by exceptions like parser configuration exception and SAX exception, which must be caught and handled. Once we have the parser, now we can parse some content. There are several inputs into the parsing process, the first of which is the content to be parsed. And so we create a new file object from the first command line argument, and then we wrap that file inside a file reader and create a new input source around it. Recall the input source is an API defined by SAX to represent the source of XML data. We'll set the system ID for the XML itself by getting the URL of the file, and then we'll call the parse method of the parser. And we send it 2 things: the XML source to be parsed, and also the handler to be invoked during parsing. And our handler is simply a new instance of our print phone numbers class. So it's that object whose methods like start element and then the warning, the error, and the fatal error will be invoked during parsing. And sure enough, when we run the print phone numbers class with the phonebook.xml file, it'll parse the XML, and the black box XML parser will make callbacks to our print phone numbers object that will invoke the start element method from which it can extract the phone numbers that are in the XML file. Sax parsing works, and it's efficient. It doesn't use a lot of memory, and it's pretty fast. And it's great for when your data is fairly simple and when you only want to do a little bit with it. But it's also kind of complex. And callback-based programming isn't necessarily natural, especially for object-oriented programmers.